Okay, so let's talk about that clock that had the minute hand, right? So the information they gave us is we have a clock. And it has a minute hand that is 11 inches long. So the minute hand is going to go from the center of the clock, right? And I'm just going to put it at high noon if you're okay with that. So I know that this is 11 inches. Agreed? And their question is, how far does this minute hand move in 35 minutes? So I'm going around, and this is about the 35-minute mark, right? So in 35 minutes, how far around does it make around the clock? How far around the clock does it make? Well, if we notice, I'm looking at the outer edge of this clock. Agreed? So I'm looking for the distance around this clock. But it's not around the whole clock, it's just around a portion of the clock. Which means we are looking for the, good, I think some of you said it, we are looking for the arc length. So remember the arc length formula, S equals theta times R, where theta is an angle, right, and R is the radius. Well, help me out. Do I have either piece of information? Good, I have the radius. The radius is 11 inches, so we're good there. What I need is theta, don't I? So, by the way, in trig, theta is like your x. That is the variable in the Greek alphabet that is used most often to denote the unknown variable when it comes to an angle. Okay, so we need to find theta. In order to find this distance, we need to find theta. So let's see, what do we know? Here's one thing we do know. We know there's 60 minutes, right, in a clock. And 60 minutes, since I'm looking for a theta, I'm looking for an angle, isn't that equivalent to 2 pi? Good, which means now that I know that, I'm looking for how many thetas, right, are in 35 minutes. This type of information is very helpful in us setting up one particular type of problem. If I have a guideline to go by, and then I've got this what if, right? This is my what if. This helps me set up a proportion. And the proportion is basically written for us already. I have 60 over 35 equaling 2 pi over the angle. So I'm just going to leave it as theta. Cool? Okay, so to solve a proportion, we cross multiply. Agreed? And now that I am looking for theta, I am going to simplify the right side. I'm going to divide by the 60, which will give us, that's right, when you reduce it, theta is equal to 7 pi over 6. Cool? Good. Which means the distance around the clock is equal to 11 times 7 pi over 6. With me? They gave us the radius. We needed to find theta. Here is how we found theta, knowing that a clock has 60 minutes in it, which is equivalent to the radian measurement of 2 pi. It helped us set up a proportion. Cool? Okay, and they asked us to round to 3 decimal places. So I don't know about you, but I ended up with, and I'm going to write it over here, in 35 minutes, my distance is equivalent to 40.317 inches. Good? Okay, so hang in there. Got another. Okay, so let's talk about the next problem. They were telling us we have 2 cities, City A and City B. So, and they told us that City A was due north of City B. Agreed? So I'm going to draw my compass. my compass, north, south, east, and west, right? And they're talking about two cities. They said we have city A due north of city B. So here's city A, and here is city B. Good? And then they've given us latitudes and longitudes, have they not? So let's look. They said city B had a 23 degree, 44 minute north latitude. So I am going to go north, right? And this latitude was 23 degrees and 44 minutes. In the meantime, they told me city A, being due north of it, had a latitude of 48 degrees and 8 minutes. And they're asking us to find the distance between the two cities. This is what they're asking us to find. Now here's the deal. When you talk about how far away two cities are from each other on the world, so to speak, on the planet, on an atlas, because since they gave us degrees and minutes, and they could have given us seconds, it's not a flat piece of paper. If you've ever seen a map, it looks like a flat piece of paper, and you should just be able to go, well, from here to here and measure it. But in reality, you're dealing with the curvature of the Earth. So if I'm looking at it with degrees and minutes, I'm actually looking for this curvature, which is the distance between the two cities. By the way, that's how a plane flies. It doesn't fly in a straight line like we're used to. That actually is a lot longer than flying with the curvature of the Earth. So little trivia for you. Anyway, so this is what they're looking for. They're looking for this particular distance. Well, if you notice, that curvature is part of a circle, isn't it? It's part of the world. Agreed? So it looks like, once again, I am looking for an arc length. And it's a good idea to write your formula down always. So I need a theta and I need a radius, don't I? Okay, so did they give me either one? Well, they gave me the radius. They said the radius of the Earth was 3,960 miles. So I know that when I plug that in, I'm going to take 3,960 miles and I'm going to multiply it by an angle, don't I? But did they give me the angle? No, they didn't. As a matter of fact, they didn't even give it to me in radian measurement, did they? I have degrees and minutes. So here's the deal. First, let's think about this. This is the amount I need to know, right? This is the amount of the angle I need to know. Is that the 23 degrees and 44 minutes? Is this amount of the angle the 48 degrees and 8 minutes? No, it's not. This angle is the difference between the 48 degrees and 8 minutes and this 23 degrees and 44 minutes, isn't it? So, to find theta, we're going to have to do a little bit of subtracting first, aren't we? So, I just gave myself a little bit more space, and I'm going to work over here. So, first thing that we need to do is find this angle. And we already said this angle is going to be the difference between 48 degrees and 8 minutes and 23 degrees and 44 minutes. Well, let me ask you something. Am I able to subtract 44 minutes from 8 minutes? No, there's not enough minutes there, is there? So what are we going to have to do? Yes, we're going to have to borrow. So I am going to borrow from 48 degrees, which is going to make this 47 degrees. And to the 8 minutes, I'm going to add 1 degree because that's how much I borrowed. Yes? But what do we know about 1 degree? Yeah, 1 degree is actually 60 minutes, which means I'm actually adding 60 minutes to the 8 minutes. You with me? Since we borrowed 1 degree, since 1 degree is equivalent to 60 minutes, then to the 8 minutes, I'm adding 60 minutes, which means in actuality, I am taking 47 degrees and 68 minutes and subtracting it from it 23 degrees and 44 minutes, which will give me 24 minutes and 24 degrees. So when you borrow, you have to be careful the units you're borrowing from. In this case, I was borrowing from degrees, so I need to add that degree to that minutes, to those minutes. But you cannot add things that are not the same, so you had to make degrees into minutes, 60 of them, so I could add it to the original minutes, which was 8 of them. Good? Okay, so I found theta, but is it in radians? Because my theta here is supposed to be in radians. Is that in radians? No. As a matter of fact, it's not even in full degrees, is it? Okay, here we go. So first, after we found theta, we need to convert to degrees. And what's the part I need to convert to degrees? That's right, the 24 minutes. So remember how we've done it before. We need to multiply by the conversion factor. So 60 minutes is 1 degree, correct? My minutes cancel, so I end up with 24 over 60, which, does it reduce? It certainly does. It reduces by 12, which gives me 2/5 degree, which is a 0.4 in a decimal, isn't it? Which means I have 24.4 degrees. So now I've got all degrees, but I still need to convert it to radians. Okay. Some of these problems are like this. You're going to actually have to do a series of steps to find the theta. In this case, I needed to subtract. And then once I got the difference, then I needed to convert it to just degrees. And now I need to convert my degrees into radians. Because the formula says theta's got to be in radians. So here's my degrees. And you're going to multiply it by this conversion like we've done before. Degrees are going to cancel. I end up with 24.4 pi over 180, don't I? Which means S is equal, to figure out this distance, out, I am going to do 3,960 miles multiplied by 24.4 pi over 180. And get your calculators out. I already got my calculator out. I find that the distance between these two cities, and let's see, they said round to the nearest mile. So when you punch it in your calculator, and I've punched it in my calculator, I have 1,686 miles is the distance between city A and city B. Cool? Okay, take this one slow. The key here is to find the difference between the two cities, angle-wise. Make sure it's all in degrees. Why? Because I have to convert degrees into radians in order to plug it into the formula. Good? Hang in there. Got another one. Okay, so let's look at this next problem. They gave us a water sprinkler. They said that this water sprinkler sprays over a distance of 36 feet while rotating through an angle of 150 degrees. And they want to know how much of the lawn actually is getting watered. Now, here's the deal. You're like, I don't really care how much of the lawn is getting watered. I get that. But you know, when you become a homeowner and you're planting your grass in the yard and you're putting those sprinklers in first, you need to make sure that your sprinklers are covering all the grass, right? So you have no dead spots in the grass. So this might be of interest to you. Maybe not now, but later. But here's the deal. If you notice, this almost looks like a piece of the pie. And you're trying to find out how much of the pie is actually getting watered. So, what am I talking about? Yeah, I'm talking about the area of a sector, aren't I? A piece of the pie. And what's that formula? That's right, that's theta over 2 times the radius squared, isn't it? Okay, so help me out. Did they give me theta or the radius? Well, they gave me the radius. They said it was 36. So I know I have theta over 2 multiplied by 36 squared. Did they give me theta? Yeah, they did. They said 150 degrees. But yes, theta once again needs to be in radians. So, looks like I got a conversion to do. Well, gratefully it wasn't as bad as the last problem, right? So, I need to convert to radians. So, you know how to do that. 150 degrees and multiply by pi over 180 degrees. We put the degrees on the bottom so we can cancel degrees, right? Which gives me 150 pi over 180. I see a fraction that's easily reduced. I'm going to reduce it. This will give me 15 pi over 18, which, last but not least, yeah, I can still reduce by 3, gives me 5 pi over 6. Good? Okay, little bit of tweak here. Theta divided by 2. Isn't that the same as 1/2 times theta? Remember, we spoke about that when we introduced the formula, didn't we? And the reason I'm saying that is because theta is a fraction. And since it's a fraction, I want to make my life a little bit easier as I am working this out. So this is a lot easier to do, multiply these two versus doing this division that we had up here. Okay, so, yep, time for your calculators. And let's see, I'm sure you have your calculators out. I got my calculator out and I got 1,696 and 46 hundredths square feet. Because remember, they're looking for area. Square feet. And they said round to 2 decimal places. Cool? Okay, hang in there. I've got a couple new formulas to introduce. Okay, so I mentioned I had a couple new formulas to introduce to you, right? One of them is linear speed. Now, linear, you already know that's basically a line, isn't it? And this linear speed, we kind of already know, except it wasn't called a linear speed. It was known as a distance problem that we have worked with in the past. So let me sidetrack you a second, okay? We've had distance problems that we've worked with, and distance equal to rate multiplied by time. Agreed? The R stood for the rate, the speed, didn't it? So if I got the rate by itself, I would take the distance and divide it by time, wouldn't I? This is something we have worked with before. Now, here's the deal. I'm going to take this formula that we have worked with in the past, and I'm going to adjust it a little bit for the linear speed based upon a circle. Now, a circle's distance isn't called d, is it? If I'm looking for the distance around a circle, that's its arc length, isn't it? Which means my formula is going to get readjusted. My formula is going to look like S over T, because S stood for the arc length, didn't it? And instead of saying R for the rate, our R is now going to be represented by V. Good? Okay. Now, by the way, if you don't know the distance, I can certainly find it because that's the formula we've been dealing with. Yes? Okay. Another formula that we're going to work with is something known as angular speed. Now, when they talk about angular speed, I'm talking about a circle still. And since it's speed, it's still distance over time. Except since it's angular speed, my distance is now a theta. It's still over time, and the speed for angular is going to be represented by W. Cool? Okay, so here's the deal. They give us a problem to look at, and the problem they're giving us to look at is the fact that I have an object traveling around a circle. The circle, here's my information about the circle, has a radius of 11 centimeters, right? It tells me in 10 seconds, which is time, it travels a central angle of 1/4 radians. And now they're asking us to find the linear speed and the angular speed for this particular circle with this information. So let's check it out. Let's talk linear speed. To find the linear speed, I need to know my distance, which is S, don't I? Did they give me the S? Did they give me the arc length? No, they didn't, but I sure know how to find it. To find the arc length, I take theta, which is 1/4. I multiply it by the radius, which is 11, correct? And then I'm going to divide it by time, which is 10. You with me? Okay, so that means my linear speed is going to be 11/4, still divided by 10. Yes? All right, so I'm hoping you remember how to divide fractions. The second fraction you multiply by the reciprocal, which means my linear speed is 11/40, isn't it? Now the units that go with this. 11, the unit for 11 was centimeters. The unit for the time was seconds. So my rate, my linear speed, is 11/40 centimeters per second. They didn't ask me for a decimal, so don't go there. Cool? Okay. Now let's look at our angular speed. The angular speed was theta, which is 1/4 radians, divided by the time, which was 10 seconds. Agreed? So, again, hopefully you remember how to divide fractions. I have to multiply by the reciprocal, which means my angular speed is 1/40. Now my units. This was in radians, and the bottom was in seconds. Radians per second. Cool? Don't make too much out of these formulas. That's all I can say. Keep them very simple. Good? Okay, so hang in there. I got one more problem for us, and it doesn't have to do with linear speed and angular speed. Okay, so let's look at this last problem. They've given us this bicyclist, right, this cyclist, and they've told us that this cyclist is traveling at a speed of 10 miles per hour. And they've given me the diameter of the bicycle wheel. It's 26 inches. And they're asking us, well, great, they're traveling at 10 miles per hour, but they're asking us to find out how many revolutions per minute that is. Are you with me? They've given us the 10 miles per hour, and they said, well, how many revolutions per minute is that? Here's the deal. that's not an arc length or an area or even a linear speed problem. That's a straight conversion problem. Because if they give us 10 miles per hour and they want to know how many revolutions per minute that is, that means we need to convert. So I'm starting with what I know. I've got 10 miles in 1 hour. And I need to take this into revolutions per minute. So, conversion time, and I've mentioned to you how I do these conversions. So I don't need hours, I need minutes. So I know that 1 hour is the same as 60 minutes. So bye-bye hours, right? Now I'm in miles per minute. And it's like, okay, well, the minutes is good, but I need the miles gone. I need to get into revolutions. So here's how I need you to think so you understand what we're doing next. 1 revolution, right? So if I think of a bicycle wheel is in the shape of a circle. And 1 revolution around this circle is I need to know how far around this is, don't I? One thing I do know, it has a diameter of 26 inches. So in 1 revolution, I guess the question is, how many inches would that be? Since the wheel is measured in inches, 1 revolution would be how many inches, right? Which tells me I need miles to be gone and inches instead. Because then I can start working on that revolution. So hang in there. At least I have a game plan. At least I know that now I have to get rid of miles and get to inches because the bicycle wheel is measured in inches. So there's a conversion that you need to know that you may not know. So make sure you write this down. 1 mile, and yes, I'm putting miles on the bottom so I can cancel it with the miles on the top, is equivalent to 5,280 feet. Well, great. At least I got rid of miles and got into feet. Well, wonderful. But I don't want feet. I want inches. And I know 1 foot is equivalent to 12 inches. Great. Now I'm in inches per minute. Well, closer. But I don't want inches. I want revolutions. Are you with me? So here's the deal. The question is this. How many inches are in 1 revolution once around the wheel? How many inches are in 1 revolution once around the wheel? I need to find the what of this wheel. I need to find the circumference of this wheel. I'm looking for the circumference because when I know the circumference of the wheel, I know how many inches I've got in 1 turn of the wheel, 1 revolution around the wheel. So circumference is 2 pi times r, isn't it? Well, 2 pi is the angle. R is 13, isn't it? Because that's 26 inches. Which leads me right back to 26 pi. Now, 26 pi is the circumference, right? What units is it in? Inches. So the circumference around this wheel is 26 pi inches in 1 revolution. Which means I am going to multiply this last part by 26 pi inches on the bottom, so I can cancel inches on the top, and that's equivalent to 1 revolution. And now I have got revolution on the top. Yep, everything else canceled, and I have minutes on the bottom, which is exactly what we want. Revolutions on top and minutes on the bottom. And now I know what I need to do between all my numbers. So yeah, time to get those calculators out. And they asked us to round to 1 decimal place as needed. So when I worked this out, this cyclist traveling at 10 miles per hour is actually, what's actually happening is I have 129.3 revolutions per minute. That's pretty fast. At least I think it is. Some of you cyclists may be going faster than 10 miles per hour, but that's a little over 129 turns around the wheel in one single minute. Good? Okay. You have fun with this stuff, and I'll catch you on the